Hello again. Let us finish chapter 5 in this video. Okay, I hope you're doing well. So let us get started. So we want to talk about 5.6 and 5.7. 5.6 is about integrals involving exponential and logarithmic functions, and 5.7 is about inverse trigonometric functions. So let's talk about exponential first and logarithmic. Now we know that the derivative of e to x is e to x. We know that. So if we differentiate, we get e to x. So if you want to go back and find the function whose derivative is e to x, it would be e to x. So that means the antiderivative of e to x is e to x. Okay, now we know that if this is u and this is u, well, of course this would be u here, right? Okay, now what about a to x? Well, we know the derivative of a to x is not just a to x, is a to x times what? Times ln of a, right? So if we want to go back this way, then the integral of a to x is not a to x. But we can make it a to x. All we have to do is what? We have to have ln a in order for the integral to be a to x. So why don't we just put ln a here, right? You know, in algebra, if you have a structure, you want to change it, you can multiply it by 1. Now 1 is something over itself, right? So here we can just multiply here by ln a because we need it to be here, but we compensate for it outside, we divide by ln a, right? So now this part, the answer of course is what? Is a to what? A to x. But since we have this extra ln a in the denominator, right, then of course the answer would be 1 over ln a and then a to x, right? So this doesn't change anything. This whole thing is still what? It's still the same as this, right? Because we just multiplied by ln a here and we divided by ln a here. But this part of it now is a to x, and then 1 over ln a stays there. Okay, so let me erase all that. So integral of a to x is a to x, but we have to divide by ln a. Why? But simply because we need to have ln a here in order for this to be a to x. But since we multiply here, we have to divide by ln a. All right, so these are two formulas, very easy to understand. So let's do an example. So evaluate this integral. So what we're going to do, we're going to make this look like that. How? We're going to do u substitution. So we're going to let u be what? Negative x squared. Negative x squared. So du is going to be negative 2x dx. So dx is du divided by negative 2x. So now we're going to take this and substitute it for dx, and then everything else, 2x we can't do anything about, we leave it. This would be e to u, and this would be du divided by negative 2x. Now the 2x goes away, but the negative stays, so the answer would be negative integral of e to u du, and that's negative e to u plus c, but what is u? Is negative x squared, right? So that's the idea. So let me give you the answer, and that's the answer right here, right? You can stop the video and make sure you got how we got from here to here by using this formula. Instead of x, you can put u there as long as everything is in terms of u, right? All right. So let's look at some application of integration. We have done few application of it, but let's do some more. One application, of course, is when we have in nature, what we are given is the rate. So we are given the rate usually, and in order to find the relationship between the variables involved, we have to take the integral of the rate with respect to some variable. Usually it's time, but it could be anything else. So this idea is very useful in application problems. For example, rate could be the rate of profit, it could be the rate of revenue, the rate of price changing, and all of that. So let's look at some applications. A price demand function tells us the relationship between the quantity of product demanded and the price of the product. So in general, price decreases as the quantity demanded increases. So usually the price demand function has a negative slope or is decreasing. As the quantity increases, the quantity demanded increases, the price goes down. Okay, so marginal price demand function means the derivative of it. In economics, they call it marginal. Maybe they don't want to scare the students of, derivative, so they call it marginal. But marginal revenue, marginal profit, that means derivative. So let's look at an example. Find the price-demand equation for a particular brand of toothpaste at a supermarket chain when the demand is 50 tubes per week at $2.35 per tube. So the price is $2.35, right? And the demand is 50 tubes per week. So what we have here is a rate. What we are given is a rate, right? So what we have to do is we have to find out what that is. So given that the marginal price, which is the rate of price demand function P prime, for X number of tubes per week is given by this, right? So we are given the rate right here. This is given in the problem. We know the rate of the price changes according to this function. How do they know that? Well, based on data that they collected. If the supermarket chain sells 100 tubes per week, what price should it set? So what should the price be if the demand is 100 tubes per week? We know that the price is $2.35, demand is what? 50 tubes per week. We know that. So let's look at that. So how do we find price if we are given the rate of it? Well, we know if we have f prime dx, we take the integral of it to find f of x, right? If this is the rate, that would be the function whose derivative is here. So what we have to do is take the integral of p prime, right? So let's do that. So p of x would be integral of p prime, and then the function that we are given, of course, is this. All right? So, so p of x would be, this number is a constant. We can bring it out of the integral. So inside we have e to something dx. Now that something, remember, we're going to make it look like this. So our u here is negative 0.01x. And if u is a function of x negative 0.01x, then what is du? Well, du is the derivative, which is just negative 0.01 dx, right? So basically it's du dx equals to negative 0.01, and then du is dx times negative 0.01x, 0.01. Okay, so dx is going to be du divided by that. So this is going to be substituted for dx, and this is going to be substituted for, we're going to put u there. This is u, right? All right, so let me clear all that. We don't get confused here. Okay, so here we go. This is the number that we had outside already. Now, our dx would be du divided by this number. We can put this number also outside, right? Because this dx would be du divided by negative 0.01. Could bring that outside. Okay, and now we have e to u and du, and we know the answer to this is just du, right? This like e to u, that's what it is. So is this divided by that is 1.5, negative over negative is positive, and e to u plus c. So that is our p of x. Of course, it's not p of x, it's p of u because we changed it to u. So what we have to do is we have to put the x back in there. So instead of u, we put just negative 0.01 x. So that's our price function. Now, remember when we solve when we get the answer for antiderivative, we always get a family of functions. Now, how do we find that c? Well, that c we can find based on the information given in the problem. Remember, we were told the price was $2.35 when x was 50. So we're going to do that. So we put x 50, and the price at 50 is $2.35, right? So c is going to equal to whatever that is, which is $2.35, minus whatever this is, because we have to move this to the left. And if you use a calculator, you can easily find the answer to this is 144. So now we have a specific function that works for, let me clear that. So this is, if I can draw a straight line, this is our price function, price demand function. That means as x, number of products demanded in the market, goes up, the price that you should charge should change according to this. So now, if x is 100, what price should the supermarket charge? Well, $1.99. Just substitute 100 for x here and put in the calculator. It would be $1.99. So the price at 100 tubes per week demanded should be set at $1.99. All right. There are some stores that computerize this, and they have wireless stickers for price in different places, and then they automatically change according to the demand. All right. Here's another example. Suppose the population of fruit flies increases at a rate of that. In flies per day, if the initial population of fruit flies is 100 flies, how many flies are in the population after 10 days? Now remember, this is a rate function, even though we don't call it g prime because we want to call the rate function g. So we're going to call the function we're looking for, whose derivative is this. We're going to call it capital G of t, right? So how do we find capital G of t? Again, we have to take this and integrate it, right? All right, now remember we had a formula that said if you want to find the accumulation at point B, accumulation of point B would be accumulation at point A, where we started counting, the accumulation, plus how much accumulation is from A to B. And then this has to be the rate, right? That's the idea. Now in here, instead of capital F, we have capital G. So the question is, how many flies are in the population after 10 days? That means, what is G of 10 days? Well, how many flies was at 0 days where we started? That many, which is we are given, is if the initial population is 100. So that's 100. So we start with 100. After 10 days with this rate, how many flies are we going to have? Well, g at 10 is g at 0 plus how many flies accumulated from 0 to 10 days. And again, this is a u substitution. We just did something similar to it. This is u, right? So du is going to be, I have it here. So dt is du over this number. And the difference between this and previous one was that previously the rate was negative. This number was negative, but now it's positive. This is increasing. Previous one, the price was actually a decreasing function. Here, number of flies is actually increasing. Okay, so the work is here, and I don't think it requires much explanation. We're going to have to find this integral, and this integral is just that part, right? That's that part. And so g of 10 equals to 100 plus whatever this is. And if you do some calculations with calculator, just put 10 in there and then put 0 in there. Notice that if you put 0 in there, this is not 0 because e to 0 is 1. So you have to take that into account. So basically you have to write 2 over 0.02 e to 0.02 times 10, whatever that is, minus 2 over 0.02 e to 0, which is just that, right? Because e to 0 is 1. And if you do that with a calculator, you get 122. So there are going to be 122 flies after 10 days. Okay? All right. So here are some formulas that we're going to talk more about in Calculus 2. But for now, one of them, this one, should be familiar. We know the derivative of ln x is what? Is 1 over x. So if you want to go back that way, what's the integral of 1 over x? 1 over x is the same as x to negative 1, right? So integral of x to negative 1 is ln x, and we have to put absolute value because we know x has to be greater than 0. Can't even be 0 because it's not in the domain of ln, right? Okay, so that is a family because we are working with real numbers. So this is a family of functions that are antiderivatives of 1 over x, okay? All right, now, of course, we know if we make this u, and you make this u, then you make this u. So u could be a function of x. As long as you have this structure, you can use this formula. All right, now this one is something we cannot do in Calculus 1. We know integral of 1 over x is ln x, but what is the integral of ln x itself? What function is it whose derivative is ln x? So in Calculus 1, I give you the formula. So that's the formula. In Calculus 2, we have to use a method, it's called integration by parts, and figure out actually how to integrate this. We're going to leave that for Calculus 2. For now, this is just an example. We can use this formula. If you have the structure, we can use this formula. Okay? And the next one is the same thing. Again, we can't do it in Calculus 1, but we have a formula for it, and notice that it's similar to this, right? If you multiply by x here, it's the same structure, except you have to divide by what? By ln a. So it's really x log base x of x minus x, just like that, divided by ln a. All right? So these two, we're going to just use the formulas. So find the indefinite integral. So we have those three formulas to work with. So by, if you think about it, if you let u be ln x, right, then du would be 1 over x times dx, or dx goes here, right? So dx is du times x, right? So instead of dx, we could just put x du, right? So instead of this, we could put x du. And instead of ln x, we put u, and the x we can't do anything about. We have to leave it there. And notice that x and x go away. Look, we have a very simple structure. We know how to do that because we know the integral of u to the first power is u to the second over 2 plus c. But what is u is ln x. So the answer to this integral is the 1/2 u to the second power. U is ln x to the second plus c. All right? All right, so now if you let u be instead of ln x, if you let u be 1 over x, you're going to see that it's not going to work, because the derivative would be like negative 1 over x to the second, and if you substitute dx, if you substitute the stuff here for dx, you're not going to be able to simplify this. So what's part of the integrand you set equal to u is important. Now, does it always work? Of course not. That's why we have calculus 2. But in some structures, this trick works, u substitution. Here's another one. This is a little bit maybe trickier. And in this case, you let u be ln x. So if u is ln of something, which is ln x, then what is du? But what is derivative of ln something? Well, is 1 over something. And then you have to multiply by derivative of something. What is derivative of ln x? 1 over x. That's how we get the structure here. And so that means from here, you see du equals to 1 over x ln x, right? dx over x ln x. You multiply the numerators and denominators. If you give a denominator of 1 and cross multiply, you get dx is that. So if you substitute that for dx and substitute u for that, then you should be able to simplify it, right? You see that? So that's our u. This we leave it because you can't do anything about it. dx is that. And now you see that goes away with that. And again, we have a simple structure which we know how to integrate. Integrate of 1 over u is ln u because we have du. Actually, you can put absolute value here. So we can put absolute, but you don't have to because we know ln here is what? It's positive. I mean, it's this right here has to be positive, right? All right. So the point here is that there are some structures that can be simplified using this trick that we just used. Okay. All right. So let's see. One more. Find the indefinite integral here. Well, here, if you let u be 3x minus x to the third power, du would be 3 minus 3x squared dx, and dx is du divided by this. And if you now substitute all of that for dx, and then all of that, let it be u, right? What's left here, we have to leave it. And we get that for dx. And looks like we can't cancel these, but if you factor the 3 out, they could be canceled, right? So factor the 3 out, now we cancel those. 1 over 3 goes outside. And again, we have a very simple structure. We know how to integrate. Integral of this is ln u times 1/3 plus c. And we know what u was. So we substitute what u was, and we have the answer. All right. All right, now we want to talk about integrals resulting in inverse trigonometric function. And I'm going to do this so we can finish chapter 5 in this video, okay? Now, we have some formulas from previous chapter. So we know that if you take sine inverse of x and take the derivative of it, we proved this in previously. So if you accept that derivative of this is 1 over square root of 1 minus x squared, if you go this way, we get that. What if you go the other way? What if you take the integral of this? Well, we should get sine inverse plus c, right? So if we accept that this is correct from previous chapters, then now all we have to do is just do some, what if we say, what if x is u over a, for a is a positive number? So if you substitute here for x, u over a, then there is a connection between du and dx. So dx is going to be, du is going to be basically a dx, right? And dx is what du over a, right? All right, so if we do that on both sides, we're going to end up with this structure. See, I just follow here. Instead of dx, I'll put du over dA. Instead of x, I'll put u over a. Now, so u over a squared is u squared over a squared, right? Now I'm gonna factor from 1 minus u squared over a squared. I'm gonna factor 1 over a squared, right? So what do I get? Well, I get a squared minus u squared. Why? Because if I multiply, was 1 over a squared times a squared is 1. Minus was 1 over a squared times u squared is u squared over a squared. So that's correct. So now, remember, this is inside the absolute value, the square root. So I'm going to bring out 1 over a squared. If I bring it out, it would be 1 over a. I'm going to leave this inside, right? Now, we also have a 1 over a here in the numerator that we can bring out. So we got 1 over a here, outside from here, from the numerator. And we have 1 over a that came out of here, right? And they cancel each other. So we end up with what? We end up with this structure on the left, right? So on the left we have that. So this is structure, which is, we just simplify it by putting u over a for x. And if you put u over a over here too, they should be equal to each other. Now this gives us a new structure. So the formula, notice, the formula here, if we only use that formula, then we are limited to what? We are limited to square root of 1 minus x squared, right? Now instead, we got a formula that allows us to do this even if we don't have 1, but we have some number a squared minus u squared. And this is the same as what? Is going to be, the answer would be sine inverse of u over a plus c, okay? All right, so that's the formula that we're going to use. Again, remember we had 3 of these formulas. We had one for sine inverse, and we had one for tangent inverse. Remember, we had tangent inverse of x prime was 1 over 1 plus x squared. And now if you go from right to left, you have to integrate this. If we integrate this, we should get tangent inverse of x plus c, right? So what happens again if we use the same trick? What if we change x to be u over a, right, on both sides? So this would be tangent inverse u over a, and see what we get out of here. Well, let's see. If x is u over a and a is positive, then dx is du over a. Again, we use the same trick we used before. This is the left side, right? So again, we have 1 over a here that comes out. Now, inside here, right? Remember, we can combine these two, right? Use the same trick that we did before. So you're gonna have to factor, you know, the same thing I did before, u squared over a squared. I made it simpler in this case. So if you don't understand previous one, so instead of 1, I can write a squared over a squared. This is a plus u squared over a squared. And now if I factor 1 over a squared out of here, I get a squared plus u squared, right? Now remember, this time we don't have a square root, so we are not going to be able to make this 1 over a. So it comes out as 1 over a squared from denominator. And from numerator, we have 1 over a. And this cancels, of course, one of these. We're going to have 2 of these, right? So we have 1 over a, and 1 over a squared is like 1 over a times 1 over a. One of them gets canceled, one of them stays here, and dividing by 1 over a is the same as multiplying by a. So we get a times that. That's the left side, right? So left side, if we substitute u over a for x, ends up being that. And the right side ends up being that. So we have that the left side is going to have an extra a here, right? And this is structure equals to tangent inverse u over a. But remember, we are interested in this structure. So in order to find a formula for that, we have to divide both sides by, a. So the formula for this structure becomes 1 over a times tangent inverse u over a plus c. Right? We got this 1 over a extra one. And so stop the video, make sure you understood what I just did here. I just substituted u over a for x, and also du over dA for dx. And just did the algebra to see how the left side and the right side compare. And I figured that they compared this way. So that means there's an extra a here. I have to divide both sides by to get what? To get answer, a formula for that structure. So we don't have to just do the ones that start with 1 or x. We can start with a squared and u as a function of x. All right, now let's look at some, they're all 3 together. The other inverses, there are 3 more inverses, but those inverses are related to what? Are related to these inverses. So we usually in textbooks, we talked about 3 of them. The other 3, which are cotangent inverse and cosecant inverse, right? And secant, all the other 3 are, they're easy to work with because there's a connection between them. Okay, so there's a connection between functions and cofunctions, right? So for example, sine inverse and and cosine inverse are related, tangent inverse and cotangent inverse are related, and secant inverse and cosecant inverse are related. And we can use those formulas. So let's look at the third one. Using the same trick I just used, you can actually prove that this structure equals to this. If we accept the original one, which we proved previously in previous chapters. Okay, so now that we have 3 formulas, we can do some examples. We're going to talk more about these in Calculus 2, but let's look at some more examples. So we have a structure here, and we have to make it look like this structure that we like, which is some number squared minus some function squared. So here, if you let u be x and a be 2, then it looks like what? It looks like this. So we know that the answer to this would be sine inverse of u over 2. But what is u? Right? If u is the same as x, then du and dx are the same. So dx and du are the same. This becomes a squared minus u squared, and a is 2, so that's u over 2 plus c. And we know u is x, so the answer is that. Okay? Now, let's do another example. Now, here again, we want to make this look like, 1 over du over a squared plus u squared, right? Now, what is a in this example? What is a in this example? Well, we have to write this as some number squared. So what squared is 2? The square root of 2. So a should be a square root of 2, and this should be something squared. So if u squared equals to 9x squared, then u is 3x, right? Because 3x squared is 9x squared. Now a squared has to be 2, then a has to be square root of 2. And remember, a is positive, so it's not plus and minus square root of 2, it's just square root of 2. Okay, if u is dx, if u is 3x, then what is du? Is 3dx. So dx is du divided by 3. So we're going to take this and substitute it here. We want to make this 3x squared, and we want to make this square root of 2 squared, right? And I have it over here. So this du goes here, and there is a 3 in the numerator, so you're going to have like something like that, du over 3. So that 1/3, we can move it out, right? All right, so now we have this structure, which looks like that. So the answer to this, of course, is tangent inverse of 1 over 3 is there already. So the answer is 1 over 3, and then 1 over a tangent inverse of u divided by a, right, plus c. And u is, of course, 3x. So 1 over 3 square root of x tangent inverse of that. Okay? And again, here's another example for secant inverse. So I want to make this look like this formula. Is it? No, not exactly. So let u be what? 2x squared. All right? U is 2x. And then let a be 3. Okay? Now, if we do that, well, if u is 2x, then x is u over 2, right? And then du is 2 dx, so dx is du over 2. So we're going to take this, substitute for dx, right? And we're going to take this, and substitute for x, right? And see what we get. So if we substitute for dx du over 2, right? And then for x u over 2, then this 1 over 2 again, this 2 right here, right? And these 2 right here, so this 2 right here and this 2 right here get canceled, because this is in this denominator, and this one goes here. If you dividing by u over 2 is the same as multiplying by 2 over u, so 2 gets canceled. So we end up with this, right? The 2's go away. You can stop the video, make sure you understand the 2's go away algebraically. And we get this. Now this does look like that formula. So the answer is 1 over a secant inverse of absolute value of u over a plus c. And that's what we get. And instead of u, we put 2x. All right, again, stop the video and make sure you follow this and you get here. All right, so here is an application where we have definite integral. So in definite integral, what do we have here? Well, we have the same structure here. It's a very simple structure. You have a here is 1 and u is just x. So we don't have to worry about changing the structure of it, except for the limits. These are x's, x values, right? So if we want to use this in terms of u, we have to change it to u. Well, we don't have to, because what? Because we already have it in a simple form. So we're going to use these as x. So the answer would be 1 over a, which is 1, tangent inverse of u over 1, x over 1. U and x are the same in this problem. And we have to go from square root of 3 to square root of 3 over 3. So this is just tangent inverse. And so we have tangent inverse of the square root of 3 minus tangent inverse of the square root of 3 over 3. So tangent inverse of the square root of 3 means what's an angle whose tangent is the square root of 3? Well, remember, tangent inverse is good only in this interval, right? From negative pi over 2 to pi over 2. And that's the restricted domain for tangent inverse. So tangent inverse of the square root of 3, what's an angle whose tangent is square root of 3 is pi over 3, 60 degrees. And what is the angle whose tangent is square root of 3 over 3? And that's pi over 6, 30 degrees. Pi over 3 minus pi over 6 is pi over 6. Like 60 degrees minus 30 degrees is 30 degrees. So the answer to this integral is just pi over 6, right? All right, so I'm going to end this video. So this is the end of chapter 5. We are going to come over here and say bye to you, and take care of yourself and others in this coronavirus situation. Make sure, now you learn calculus, you know that we don't want the increase of coronavirus cases to be exponential. And if it is, then exponential, you understand exponential function, it grows really fast. And so if you have 2,000 cases today and every 3 days it doubles, then in 3 days you have 4,000, and in 3 more days you have 8,000. So you don't want to do that, because the capacity of the healthcare system will be completely passed by a number of patients. All right, so take care of yourself and others, wear your mask, and make sure you do social distancing. 80% decrease in number of cases if you do that. All right, take care of yourself and others.